Hello and welcome everyone. In this day 28 learning of expressions and binary tree types, we are firstly going to be starting out with expressions in binary trees and the way that we represent it, right? So we can represent uh, an expression in binary tree where a node holds operand or operators. Like for example, there can be this expression. This can be represented as, let's say, this is a form of in order expression, and this can be represented as this way, with the the root node being an operator. If it is an operand, then we can simply return the value. Here plus is an operator, while 3 and 4 are operands, while plus is an operator. Operator, these two are operand, right? So similarly here 5 and here is 2, right? So this expression can further be represented in many different ways. Like the one we have seen here is in order fashion, in order expression, which is nothing but 3 plus 4 into 5 minus 2, right? Similarly, we can even have uh, post order. Post order and pre order. A post order is where we have uh, the expression at the end, and similarly here 5 2 minus, and finally a multiplication. And pre order is where we have expressions at the beginning, and then we have the operators at the beginning and the operators at the end. So these are the different ways of representing this specific expression, right? So next thing is we can even uh, have these expressions uh, being calculated or evaluated and even transpile them or manipulate them using stacks. We can create such expressions using stacks where, let's consider post order as an expression. Let's say if we use stack, so if we get an operator like uh, so let's take building from build post order. We have seen this example quite a few times, like for example 3 4 plus 5 2 minus, and finally a multiplication. Let's say if we see an operand push to stack, if operator like plus minus multiplication or division or any of these, pop to nodes from stack. So this is what it is. So with this way, with this idea, we can even have an implementation of post order expressions, and we can even evaluate them. So let's look at how we can build a code around this, right? Let me switch to VS Code. Let me switch to JS Mint to showcase this. Okay, so here I have written the expressions and uh, where they are really used. Compilers use them to represent and evaluate expressions. So we had taken this simple example. This is uh, of this representation is simply an in order or infix way of expression representation, and the way we even talked about this where we can build this post order expression with the help of stacks, and we just talked about this logic here. So uh, here we have a simple expression node which has a value which is nothing but an operator. The left and right portion of it would simply be operands or the numbers that are required to be uh, operated upon, right? So we have these set of operators, and build from postfix is the one that we were seeing, right? So uh, we build, since postfix will have operators at the end, and it will always start with two operands. So if there is an operator, we create node, we pop the two nodes which is right and left by popping two times and assigning the values here as seen here. And if it's not an operator, we consider it as an operand or a number, and we push them to stack until we find an operator, right? So this is the way that we build binary tree expression with a postfix string, right? So here we have many other different ideas with uh, a prefix type of notation, and also we have some evaluation methods also, which should be very easy to understand. I would just paste this code snippet, and you can definitely check this code out and explore more on what this is doing, and maybe spend some time around here, right? So yeah, let me try running this code and let's understand what's going on. So if you see, I have bunch of driver code here where I have built this postfix expression and infix expression binary tree, and infix, and many other things, like we are even able to transform postfix to infix, prefix, and again postfix, and also evaluate the same. So yeah, this is about a different set of operations or possible things that we can play around here, right? Okay, so now we have completed the expression trees, at least with some basic knowledge on it. Let's move on to the next topic that we had planned here. So next would be binary tree types, right? So let's start it off in a new page. There are plenty of binary tree types, but we are going to looking at one specific tree type, which is AVL AVL tree. AVL tree. Adelson Welsky and Landis. right? So, and this is one type that we are going to be looking at, and there are many other tree types. Maybe we will focus on this one, and the other ones maybe we will have code snippets around and just some basic definitions that we are going to talk through and just provide code snippets just to go through it, right? It should be pretty much easy to understand once we have this specific piece uh, understood, right? Once we understand this one, red black tree type, and we have B tree and splay tree, and we have augmented trees. Inside this, there are again order statistics and interval tree, interval or segment tree, and next thing is scapegoat tree. Few of these names are really funny, so yeah. But as we said, we are only going to be focusing on this one, and maybe we might throw in the code snippets around all for all of them, right? And maybe a brief set of definitions for these. All right, so now let's start looking at uh, understanding AVL tree and what it is, right? So so before even understanding about AVL trees, we have seen binary search trees where there might be full balanced trees where there are all nodes to a specific child, and uh, might be containing one leaf node or two leaf nodes or no leaf nodes, right? So there are different terms for each of them. So if we are going to talk about a fully balanced BST, so there is going to be height of let's say root node and left portion and right portion of node. So these two are again going to be fully balanced, where each of the node either each node either contains one or two or zero nodes. Same for this one. So and height of each of them, let's say height of each of them, both of them will be n. So that's when we call this as a binary search tree. In case of AVL, the difference between height of left portion minus height of right portion is going to be 1, right? So this is the most important step. Or one of the portions is going to have one less than the other portion. So that's what makes this an AVL tree. So there might also be few imbalances or variations or violations that might come about when working with AVL trees. Like for example, let's say there is uh, one greater node, or there is imbalance in the left side portion, so we can have left rotation or moving one left node to the right node to make the difference of left and right portions to follow this property, right? And similarly we can also have right rotation if there is height of right, which is uh, being one greater node or two greater node than the left portion, and to balance or to make the AVL tree we can have a right rotation. There might be other combinations such as uh, these are part of single rotations. There might be other double rotations like left right, left right rotations, right left, and combination of them left left or right right. Many such rotations can also follow. But with this understanding, let's stop AVL tree discussion and let's quickly move on to uh, the JS bin, just to quickly walk through whatever code that I have. And there might be other tree types as I mentioned. I will just paste the code snippets and you will find a description with the code snippet, something like this, just to showcase. So you will find the specific tree type and also the different definitions that the tree has, and uh, the different information that are required to understand with that specific tree. Like here there is a balance factor, so this is perfectly balanced tree. Like here there is left side is greater, which definitely makes it a AVL tree, and this has a left dominance, so left rotation is required, right rotation is required, and also describing the different types of rotations here, right? So yeah, so you can definitely find such uh, uh, information. Please do check out the VS Code GitHub link pasted in the video description. I will stop this video for now. Hope you found the explanation with all the three topics that we had so far. Next, we will be starting with graph topics in data structure. Hope you found this video helpful. Please do like and subscribe to my channel. Thank you.